So before I forget, because I was going to mention, there's like a nice application of the fixed point theorem that I didn't say yesterday, but it's still like a interesting one to see because it can be a bit counterintuitive. So maybe I can show you that first. Um, let's see. So here's like the application. So essentially, I mean, it is doesn't quite fit. Like the context that we have been discussing because we were discussing the theorem for a function of one variable. But I think I had said this before, like there are versions of the fixed point theorem for like functions of two variables or three variables, like, like they're generalizations. So here, like the idea is like, imagine you have like a city, which is like being shown here, like in the animation in some way. Um, So you have like a city and you create like a map of the city, right? So for example, here's like a map of the city, like I can increase the opacity so to make it better. So yeah, like you can have like a map of the city and you can place it anywhere, right? But if you think about it, like at least at a first glance, like what does a map do? Like if it's like a accurate representation of the city, like it will shrink the distance between all the points in the city, like by a certain amount, so that it's like an accurate, so that it's like a more like convenient representation. But like the idea is that one way to create like the map would be to, whatever the distance, like the true distance is between 2 points on the city, you kind of like in the map, I don't know, do 1/1000 of it, or like you just like shrink everything by a certain amount. So, what from that perspective, you can think of a map as some sort of like contraction, because essentially you're like if you think of the map kind of as the image of the function, like the function being whatever takes a point in the city to the corresponding point in the map, then the map is kind of like a contraction. And so, like, there is a version of the fixed point theorem that says that if you place the map on somewhere on the city, then there will be at least a point that gets fixed where, like, the point on the map literally is on the same spot as the point on the actual city. So it's kind of like a fun, like, I hear like the animation is showing you what the fixed point would be, but it's kind of like I mean, if we hear like for the first time, it sounds very counterintuitive because it's saying no matter where you place a map, you know there's a point on the map that is literally on the same spot as the point on the city. So again, it has nothing to do with our fixed point because our fixed point is just for functions of one variable, but it is really like the same idea like of the fixed point theorem. It's just for a version of a function of two variables basically. um so, I mean, if someone wants to play with it, I can put the GeoGebra link on that Zoom chat. But I thought, like, oh, that's like I mean, there are many fun applications of the fixed point theorem uh, of that sort where, like, they're kind of like counterintuitive. So that's kind of what's nice about the theorem. So I thought I should at least mention it before I forget about it. Um, then, what we do have to talk about today is another method to find the zero of to solve like an equation, which is called Newton's method. So or Newton Raphson. So Newton kind of like came up with the basic idea. So what I was going to show you first is kind of like an animation of how the method is supposed to work, and then we'll kind of like write some details and see why the method should work under certain circumstances. Okay. But since I'm still on GeoGebra, I might as well show you the animation first. Okay. So here's like the idea of like Newton Raphson. So kind of let me see if I can zoom in just to make it more clear. So the idea is that you have a function, right? In this case, the function is x squared minus 6 in the animation. So you have a function and you want to find where the function crosses the x-axis, which is kind of like the same as like setting it equal to 0. So you want to find a zero of the function, which in this case would be like a zero of this polynomial. Again, because it's a polynomial which is quadratic, you could do that like just by like using the quadratic equation. But like the idea is like think about it in more generality, where you don't know how to solve the equation. So the idea of Newton Raphson is like a way to to try to find the zero of that function. Okay, so I'll show you kind of what the idea is like, and then I'll write it down on the tablet. So the idea is like, again, kind of like we very similar to how most of these like methods work. You kind of like start with some random point which which has no connection to the zero. Okay, so like in this case, like the random point, the random value you start with is like 3, which is what you see here, like x naught equals 3. Okay, so you start at x naught equals 3. That gives you a corresponding point on the graph, right? And then what Newton Raphson does is you find the equation of the tangent line to the curve or to the function at this point, which is what I'm about to show you here. Okay. So I don't know if you can see here, like there's kind of like this line segment. Okay. So you use the tangent line and you instead of like, and then you follow the tangent line until the tangent line hits the x-axis. Oh, well, it's not related to the fixed point theorem per se. It's like just like another wet method to find a zero. Although we'll see later that actually it can be rephrased as a fixed point problem, but not initially, right? Because initially it doesn't seem related to it, as you're saying, but it will become related to it, but later on. But for now, it's kind of like you're trying to find the zero of a function. You're trying to find where a function is zero, and this is like a way to do it. Like we already had discussed like the bisection method, if you remember, like on Tuesday. So the bisection method was one way to try to find where a function becomes zero. But this is like an alternative. But yeah, it will be related to the fixed point, but that is not clear at the moment. It's just like kind of like a different thing, which actually kind of like since Newton came up with it, it's kind of like one of the original methods for finding a zero. Because I mean, like it basically came up at the same time as calculus was developed. So it's kind of like one of the original methods. So I think there's like a lot of historical reasons why this method is still uh, discussed, like in a course on numerical analysis, because it's really one of the first ones that it was ever found. Uh, but the idea, but kind of like it's like a very geometrically, it's a kind of like a nice idea. Like it's as I was saying, you start with a point um, for x. You start with a value for x that gives you a corresponding value on the graph on the function. Then you use a tangent line. That tangent line will intersect the x-axis at some point. Okay, which is it's like this second point that you see here, and then you repeat the process, kind of like as all these methods are supposed to work. So for this point, you find the corresponding value on the graph of the function. Then you find the tangent line, okay, which is this one, and then you use the new tangent line to find a new point, okay. With this new point, you find the corresponding point on the graph. Then you will find the tangent line of that point, and you kind of like keep iterating this process, repeating it. And what you like again, kind of what you would like to see is like under what circumstances like this actually converges to the zero of the function. But that is kind of like roughly what the idea is like in this method. Um, but I wanted to show you like an animation first, so that so that you would see how it works. Like, let me see if I can start with something else, just to kind of like illustrate it again. Like if I started, what if I had started with 1.5, for example? Okay, so if you start with 1.5, it gives you a point on the graph. You look at the tangent line. Okay. Okay, so now the tangent line, that's the tangent line here. It takes you to this point on the graph. So you have to go up a little bit, like the point is somewhere in here. Then you would find the tangent line to that point. Okay, and then kind of like iterate. And so like, but it's kind of like the idea is to use like the tangent line to kind of like find the next point on the x-axis. That's kind of like the idea. Um, and of course, like, you wouldn't expect this to work every single time, because what if you start with a point that's too far away from the zero and things like that. But that's kind of what we're going to try to understand now, like when does it work and things like that. Okay, so let me see if I can write some of this stuff. Now, So yeah, as I was saying, where this is called Newton Raphson, and this will be a method to locate where a function is zero. So let me draw a picture first. So let's say that I'm like, there are like a couple of places where this particular function is zero. Like there's like a zero here and a zero here. Let's say I wanted to locate this zero. So I'll usually call like X star the important points that we're talking about. So X star here is like a zero of this function. So this is a value, a point where f of X star equals zero. Okay. And so the goal of Newton Raphson is to try to find that approximate, as always, create like a sequence of values that get closer and closer to this particular point. So the goal is to construct a sequence xn which converges to x star. Okay. And so, kind of like the sequence will be made in the way I was explaining a couple of minutes ago on the animation, but like there are two assumptions that we're going to make. Okay, so the two assumptions to kind of like get this started. So the first one is that kind of like we already know that the function has a zero. So like we already know that x star exists. Like again, that sometimes you can guarantee because like sometimes like the function is positive and sometimes the function is negative, and we know if the function goes from positive to negative or negative to positive, it had to be zero somewhere. So we this method doesn't try to show that the zero must exist. It's just already assuming, starting from the assumption that there's a zero. So we kind of like will assume that x star exists to begin with. Okay, we will assume uh, and the other thing that we will assume, which is kind of like being represented in this picture, we the other thing we will assume is that the derivative, and you will see this one appear like in a moment why that's a convenient thing to assume, but we're going to assume that the derivative at that particular point of the function is not zero. Okay, so we will also assume okay. So the derivative, so what happens geometrically if the derivative is not zero is that kind of like the tangent line is either positive, like, it's increasing or decreasing at that point, right? Kind of like in this case, like the tangent line is increasing. What would happen if the derivative were zero, right? If this had been zero derivative, is roughly that the function is too flat. If the derivative is zero, that means that the tangent line is horizontal. So it's kind of like the function is very flat near at that point, and so you wouldn't expect that method to work really well because, like, then the graph is almost horizontal at that point, near that point. So like, like it may be hard to locate the zero. Uh, But let me write that as kind of as an aside. Like you don't want the graph to be very flat near X star. So this avoids. Yeah, so like in something like that, then like the way I'm setting it up, you wouldn't be able to apply this method directly to that. Like I mean, there is like variations of this method in other circumstances, but I kind of like doing kind of like the most basic one, where like this assumption will be used. So it's not like this method is a little bit different from the other two that we have talked about because it's not as guaranteed to work as some of the previous two that we had discussed. So, uh, well, it said it depends on like it depends on what you like. The thing is like it always depends also like on the starting point, right? It's not that um, like because like the idea is like the starting point matters as well. So like even if you have something like y equals x cubed, sure, if you had started that sequence at zero, then obviously you got stuck there forever. But like you have to imagine what if you had not start the sequence at zero, you know, then that what we're talking more is about like conditions. We're kind of like thinking about conditions that would give you some sort of certainty that the method would work. It's still possible that for the method to work under other situations, but not because it's guaranteed to work, just because it happens to work in that particular case. But yeah, if you take something like so like what I'm trying to say is that so this method wouldn't apply directly to something like x cubed for x equals zero. So but it's fine because it's not we're not trying to make this work in every single circumstance. That's what I'm trying to say. Um, so like so it can be applied directly to something to like let me see actually if I give me a second, maybe I can try to do that. Yeah, this is not like a super wait. I'm trying to find if I can. Wait. Um, I'm trying to find like in the anim if I can show you the animation what how it would look like on X cubed. Okay, so actually let me go back to the animation for a moment um to show you what's going on happening here. Um can everyone see GeoGebra? Um so like for example like what I'm trying to say is that if you take something like y equals x cubed, right? Um Then, like, if you kind of try to apply the method here, like the idea is like you start with the initial point, like x0, again, and you do the thing with the tangent line that I was telling you about. So you start with x0 here, gives you a point on the curve, which then you use a tangent line to find this the next x value. Then it gives you a point on the curve. You use a tangent line to find the next value. Then and so you keep repeating it, right? But if you can see here, like if you, I don't. Oh, yeah, I'm trying to zoom in so that you can see. Like it's kind of like y equals x cubed. As I'm saying, it's kind of like roughly very horizontal near the x-axis. In fact, it's even worse than that because also like the second derivative is zero at y equals x cubed. So it's not just like the first derivative that's zero. It's even also the second derivative that's zero. So if you see, like, I mean, kind of like the method, like if you kind of follow of the method, like it still kind of seems to be, kind of giving you points closer and closer to the origin. But kind of like what I'm trying to say is that in this case, it's a bit more problematic because it could happen that it kind of like gets stuck. Would like to try to get stuck before like um, reaching the zero because like kind of like the graph is too flat. So it could still work, but it's not as guaranteed to work. And we're talking more about situations where you are guaranteed to work. So like sometimes like that's the thing with these numerical methods. We're kind of like worrying about the worst case scenario, which is what's the worst thing that could happen. But then sometimes like the method kind of like works like outside like the kind of like the conditions that will guarantee that it works, you see. So it's more like about, and you'll see where like the condition of on the derivative appears um, in a moment once I write this down. Well, the reason why we're doing this method, like I mean, like it may not seem like super exciting to work on this method because it seems like it has more extra assumptions. The reason why we're doing this method, which I'll tell you about in a bit later once we talk about what we set it up, is that if it works, it can converge faster than the previous methods. So if for some reason you know that the method will work, then the it approaches the limit faster than the other ones. So it's kind of like has faster convergence. And we'll see that in a moment as well. So it kind of like converges to zero, not to zero, to the limit point faster. So that makes it useful despite the fact that sometimes like that it may require like extra assumptions, you see. So what was I saying? Okay, so how does the method work? So here's like the idea of the method. Let me see if I can copy it. So how is the sequence generated? So again, kind of like as always, you start with a first point which is completely like arbitrary. Like think about it as being arbitrary. So let's call this x1. But once that one, the starting point is arbitrary. But once that one, you start with that, like everything else is fixed. So what I'm saying is that um, actually, let me see if I can find something a little bit better. I'll find one that looks a bit more realistic because otherwise, like the tangent line won't look that great. Mm, let me see. I mean, yes, like actually, let me redraw the graph because otherwise, like it won't look that great on the. Okay, I'll exaggerate it, but like say this was x1, um, this was like x star. So the idea is that with x1, you find the tangent line again. Like the tangent line won't look quite tangent, but it's kind of hard to make it work. Like to draw it here, like so that it doesn't look like literally on top of the zero. So kind of like think of this as being the tangent line to the fixed point. Not the tangent line to the fixed point. I meant to the tangent line to the curve. Sorry about that. Okay. So what is the equation of the tangent line? That's what you need to find. If you remember, like the equation of a line is y equals mx plus b, right? Or you can also write it as, you do have this point. This point is the point x1 comma f of x1, right? So there's like another way to write the equation of the line, which is y minus y1, right, equals m times x minus x1. Those are like the two versions to write the equation of the tangent line. The second one is a bit more convenient because we do have like one of these points explicitly. So that gives you y minus f of x1 equals m. What is m? It's the slope of the tangent line, which is the derivative, right? So it would be the derivative at that point. So that would be f prime of x1 times x minus x1. Okay? So that is the equation of the tangent line. And what you try to see is find a value of x for which this line crosses the x-axis. So you want to find where the line crosses the x-axis, and that would be the second point in the iteration. So you find where the line intersects the x-axis. And that becomes x2. So x2 is going to be this, maybe I should use a different color. X2 is going to be precisely this point where the line crosses the x-axis. So how do you find x2? Well, at x2, the y value for the line has to be 0. So you just get in this equation that 0, right? You just plug y equals 0 there. And so you get that 0 equals f of x1 plus f prime of x1. Where does this happen? At x2. That is going to be called x2 minus x1. And you see, if you that gives you an equation that you can solve for, x2. So you get the minus f of x1 equals f prime of x1, x2 minus x1. And then you divide by the derivative. Right, and that gives you the equation for x2. So x2, you add one x1 to both sides. Sorry, you add x1 to both sides, and this gives you this formula. Is it making sense how I found the x2 value? So you start with x1. You start with x1, that's arbitrary. That gives you a point on the graph. You find the equation of the tangent line to that point. This is the equation of the tangent line. Is that making sense? Then you want to find where the tangent line, you want to find the point where the tangent line crosses the x-axis. What does it mean for a line to cross the x-axis? It means that its y value should be 0. So you replace this with 0. So what I did was plug in 0 here, and that gives you an equation that I solve for x2. Because like where this crosses the x-axis, that's that point, that value for x is what I'm calling x2. So that gives me like an equation that x2 must satisfy. Is that oh, why? Because what is the equation of a line? It's just like what is like the equation of a line in general? If you have a, you know, I can put it here. If you have if you have a point on the line x1, y1, and x comma y, what is the equation of a line? It's y minus y1 equals m times x minus x1. I mean, you will get the same. It's just that you have to find that intercept, right? And so how do you find b? Like, b will come from basically the same formula. Like, the thing is like you don't have the b here, right? So you would have to find b first. Uh, and how do you find b? You use the fact that x1, like it's just like sometimes like this is like a more convenient version of the line. This is like a more convenient version of the line equation if you know a point on the line. This is a more convenient version if you know the intercept, but I don't know the intercept. I mean, you can find it once you know a point, but it's kind of like going back in circles. Like it will give you the same. Um, is that making sense? And the idea is like once you have x2, you would repeat the entire process. So at x2, again, it's hard to kind of like draw it here, but x2 gives you a point on the graph. You find the tangent line there, and then where the tangent line hits the x-axis, that becomes x3. So kind of like the sequence, the way the sequence is generated, instead, like x1 was arbitrary, then x2 was x1 minus f of x1 divided by f prime of x1, and then x3 is exactly found in the same way, but with like in terms of like the x2. And the same goes with x4. What would be x4? It would be x3 minus f of x3 divided by f prime of x3, and you go on forever, for eternity. And so what is the formula for xn? The formula for xn would be xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1. So that is the formula for the sequence in the Newton method. Is that making sense? Like what the formula for the sequence? Any questions up to now? And then, Now notice the following. What if now what I have to like kind of like address a little bit is like when would this work, right? When does this sequence work, right? So for now, first thing, like let's notice what happens if you know for some whatever reason that the sequence converges, right? What can you say if you know that the sequence converges? Because as I said in class before, kind of like you should always think of these problems as two steps. First, like you worry about the sequence converging or not, but then if you know convergence, what can you say about the limit? Okay. So for now, let's assume that the sequence converges. What can you say about the limit? Okay. And then I will return to what when can we say that the limit exists? What can we say in this case? Well, and what can you say in this situation? That's why you know uh, knowing that the limit exists is very useful because then you can just apply limit to both sides of the equation that defines the sequence. So since xn is xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1, if you take limits to both sides of this equation, then that means that the limit of xn, would be the limit of xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1, right? But what is the left-hand side? That is just the limit of the sequence, which usually, and again, I'm calling the limit of the sequence as x star. So x star would be the limit. Okay. And then how do you evaluate this limit? The limit, this one exists if the function is continuous, which it should be because you're even taking derivatives, right? If the function and the derivatives are continuous, like that will be important. But if both are continuous, then you can also evaluate the limit just by moving it inside. So this would be x star minus f of x star divided by f prime of x star. Okay. So the x stars cancel, right? So you get that 0 equals minus f of x star divided by f prime of x star. And you see, like that is why it was important, that to know that the derivative would not be 0 at x star because like that is like what you would need for to assume that like 0 is like f of x star, right? So indeed, it would be like like it will have like the property that you wanted, where like I mean, in fact, like in this, kind of like implicit in all this sequence, for this sequence to all work, like implicitly, you like this method would collapse if at some point you happen to be unlucky and the derivative like vanishes like at one of these points, right? Because then you're dividing by 0. So I mean that could be one of the you know like the things where that could go wrong, but but like so like it's a bit but like if that doesn't happen, like this is fine, and this would be that would be saying that 0 equals f of x star, which we kind of already knew. So that this is consistent with with the fact that like that we wanted like a 0 of the function, right? So this is good because we wanted a 0. This is good. Uh, but okay, that is all like under the assumption that we know that the limit exists. What's a bit more interesting is when can what guarantees that the limit exists, right? So like a more important question is when do we know that this limit exists? Okay. Okay, so again, let me just rewrite the sequence. This was the formula for the sequence. It was xn equals xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1. Okay, so that is the formula for the sequence. Now, it's actually interesting, and this kind of goes to one of the questions at the beginning of today's class, where I kind of briefly mentioned, oh, this is actually related to a fixed point theorem, but it's not super obvious at the beginning. So, kind of to see the connection, what you can do is define a new function which is related to this formula. So, what I'll do now is define a new function. I'll call it n just for Newton. So I'll call it n of x is going to be x minus f of x divided by f prime of x. Okay. And the nice thing about this function is that kind of like if you write it that way, um, if you use that function, then the sequence can be rewritten in a nicer way using this function. Is that making sense? And that like that is the same sequence as the one that we had before. But what's interesting about this, if you rewrite it this way, what's interesting about it, what's interesting is that that is precisely how the sequence was constructed yesterday when we were trying to find a fixed point of a function. So this sequence is like the same sequence that you would be trying to construct if you were trying to find a fixed point for the function n, not the function f. Okay, so this is the same sequence. One would use to find a fixed point of n. That's the important thing. It's not a fixed point of the function f that I started with, but rather of this weird function. Yes. So what that tells you, what this tells you is that what that tells you is that, and in fact, no, what would be a fixed point of this function actually? Like it's also useful to notice that a fixed point would be a zero of the function, right? F. Notice that as notice that if x star equals n of x star, right? Then that means that x star equals x star minus f of x star divided by f prime of x star. Right, so that it's kind of like a fixed point of n would actually correspond to a zero of f. So So, like, what I'm trying to say is that really, whether Newton works or not, boils down to whether the function n. What you would like to know is whether the conditions of the fixed point theorem applies to n, whether that works or not. Like, because we had from yesterday the fixed point theorem, so we could try to apply it to n. Okay, so we want to know. So it kind of all boils down to whether the fixed point can be used to n. So we only need to know. I don't know, anyone remembered from yesterday what is an important condition that we had to check for the fixed point theorem to work? So for the fixed point theorem, what you want to check is whether the function is a contraction or not. That's kind of like the easiest thing to try to. If you have a contraction, then the fixed point theorem basically kind of like works. So we want to know if the function is a contraction. Okay. But what did we check for like a contraction? Like to check if the function is a contraction, a useful property would be if the derivative is less than one, right? Like that's like the property that we had. So okay, but what is the derivative of the function? So n of x is x minus f of x divided by f prime of x, right? So what is the derivative of this function? So the derivative. Okay, so how do you find the derivative here? It's a derivative of the first term minus the derivative of the second term. How do you find the second derivative? You use the quotient rule, if you remember that from Calc 1. Um, so it's minus the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared, right? So that is the same if you use common denominator as what? And then the first two terms cancel. So you end up with this useful formula for the first derivative. Is that okay how I found the first derivative? So, okay, so then you are like, okay, how do we know whether this, well, be careful because you cannot cancel these two because this one is the second derivative, right? And this is the first derivative squared, which is different, right? The first two terms. Oh, like by the first two terms, you mean these ones? Oh, yeah, yeah, yeah. There is a plus. Yeah, yeah, yeah. No, no, you're good. You're good. You no worries. Like yeah, if you want like another version of writing the formula, um, if you prefer, I may actually may look a bit more confusing, but sometimes like the first like the prime notation, like if like I think people usually prefer to write it in the prime notation because if you write it this way, you see that it looks a bit too messy, you know. Um, But that kind of gives you like the formula for the first derivative. So what we would like to know again, to have a contraction, the important thing to remember is that for a contraction, you want the first derivative to be a constant less than one, right? For, for a contraction, for k is a constant less than one, right? And so and then you can okay, and then this is like the what's this a bit of it confusing because you are like, okay, this is the formula for the first derivative. It's not super obvious whether this is like less than one or not. And I agree with that, but that is where you have to go back to the assumptions of the theorem because the assumption of the theorem was that somehow, you know, that somehow you knew that you had a zero of the function f where the first derivative of that zero was not zero, right? So we kind of like do have to assume that, you start with a zero of the function. If you assume that, then you can evaluate the derivative there. What would be the first derivative at x star? So notice that m prime of x star, what would be m prime of x star according to this formula? It would be f of x star times f double prime of x star divided by f prime of x star squared. Okay. And these that the first derivative at x star would be zero then, because f of x star is zero by assumption. So all of this gives you zero. And so, what does that mean? It means that like we don't know, like maybe let's try to draw like a graph of like we don't know like how nx looks like, but here's like a graph of nx. You have x star somewhere in here, and the first derivative is zero at x star. That means that for um for n, x star is kind of like a critical point. So x star is a critical point of n of x. Okay. So if you draw the function n of x, or let's say if you draw, like, let's draw here the graph for like n prime actually. So I don't know, like, you don't know what the graph for n prime of x looks like. That's for sure. Like we don't know what it is. But the only what we do know is that at x star, that the function n prime is zero. Okay. So at least this part is accurate because at like an x star, like the function, like the first derivative is zero. So like again, this is a graph of the first derivative, not of the function. So if the function is zero here, at least you know, near x star, the function, the first derivative will be less than one, just because of how continuity works. So there will be like kind of like an interval. If this is like one and negative, let's say this is one and this is negative one, and then let's say this is like, I don't know, if you wanted one half, just to give you some wiggle room, if this is one half and this is one half, or minus one half, there is like an entire region. There's kind of like all this safe zone where the first derivative will be between negative one half and one half. So by continuity, basically, there will be an interval near x star where the first derivative is still less than one half, and that gives you like a contraction, basically. So since n prime of x star equals zero, and this is a contraction. So what that means in general, I mean, this is just to kind of give you like an idea of what are the conditions that go into making the theorem work. In practice, like you kind of like just, if you want to use Newton Raphson, you kind of like just use it, and you see whether it works or not, because like these conditions are hard to check in practice sometimes. But kind of like the idea is for the method to work, what you want to do is start the algorithm with a point that's close enough to x star, because that will guarantee that there's a contraction of the function n. So let me like just like wrap this up by summarizing it like that. So for Newton Raphson to work, you start the sequence. Okay. Um, and that is kind of like the idea behind the method. Um, let's maybe take like a 5 minute break, just to see if there are other questions that like show up, because like after that, uh, you have to we have to talk about something else. So the idea is that to say, okay, what does it mean to say that n is a contraction? It means that to say that n is a contraction, you have to say that the derivative of n is less than one, right? Okay. What you do know, what do you know about the derivative? What do you know about the derivative? You know that it is zero. You know that the derivative is zero at x star. Is that making sense? So if that's why I'm drawing the graph of the derivative. This is the graph of the derivative, right? This is the graph of the derivative. Like the derivative is well, I'm not saying that it is one, but why at x is it one? I'm not saying that it is one at x. What I'm saying is that if you look at the if you draw the graph of the derivative, what I'm saying is that here's the graph of the derivative, right? I know for a fact that the derivative is zero here, right? Uh, but the derivative, if you assume that the derivative is a continuous function, right? It cannot go from zero to like 100. It cannot jump from 0 to 100 in no time, right? It has to grow. It takes some time to grow and uh, increase or decrease. So, you know, if the derivative is zero here, it must be less than one on some interval, because like that's how continuity works. That's what I'm trying to say in this graph. Like, I'm not saying that I'm not writing anywhere that at x is it one. Uh, I'm saying that because it's zero here, it cannot go from 0 to 5. In like it always needs like that's how continuous functions work. If you have let me see if I can draw it here somewhere else. If you draw a continuous function, like ignore that this is like a derivative. You know, if you have a continuous function, uh, if you have a continuous function which happens to be zero at some point, right? This is where like the function is zero. Then there will be an interval where the function is between -1 and 1. Just because of how continuity. Oh no, at zero, like at x equals zero. Oh, I'm not saying that at x equals zero is one. Like I mean, like I don't know that. I'm just trying to draw a graph. Like I mean, in fact, at x equals zero, it looks to be here. Like it could be one, it could be less than one. I don't know what it is like at x equals zero. I just have to draw. Oh, I mean, I just have to choose something less than one, like so it's easier to draw one half. But you could call this k if you like. You know, if you want, you can call this k. You know, It's just like some number. I mean, it depends what you mean by concrete math. It's just like I'm just saying that when you have you have like a function that is zero here. If you have a function that is zero here, if it's zero here, it must take some time to go beyond one. It cannot immediately jump from zero to one or something like that. If a function is zero and it's continuous, it can, like, there must be some interval where the function doesn't grow too much. That's kind of what I'm saying here. But I don't have enough details, I don't have enough details to say how big this interval is, or I don't know, like, or what the value is at zero, like, all those things I don't know. So those things are not concrete. Yes. I'm just saying that if the function happens to be zero here, it could not, it has to be close to zero for a little while because, that's how continuity works. So, I mean, we're not assuming, like, I mean, the only thing that I'm assuming is that, like, the function is continuous because if you have that the function is continuous, then if it's zero somewhere, it cannot grow too fast, basically. Uh, you know. But yeah, I don't know the specifics of this graph. So, like, this graph isn't, I'm not claiming that it's, like, accurate except for the fact, the only place where this graph is accurate is in the fact that it is zero here. Except for that, I don't know how it looks like. Uh, let's Okay, well, as I was saying, let's take a 5-minute break because that way I feel like I can answer better if there are any other questions about this or something else. And then once we come back, I'll tell you some other, like a small thing about error, which is also useful to know. Uh, so let's say 11:45. Let me stop the recording. Okay, so the last thing that I was going to tell you about today is a bit about error estimates because like if you notice what we have been doing this week is that there was like a point that was useful for us, like maybe where the function becomes zero or where the point is a fixed point for the function, and then we constructed a sequence that approaches that particular point, right? And so what you would like to know when once you know us that there's like a sequence that approaches that point, you can still ask how fast does it approach that particular point. So you want to know kind of like the 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 speed of convergence to the given point because that's actually very important in algorithms to know. So that is related to estimating the error in the approximation. So like I'll tell you a little bit about error calculations. Okay, so suppose that you have a sequence that converges to a point x star. Okay, so here's like the setup. You have a sequence xn which converges to a number x star. So the error, like the error in approximating that point is kind of like how much like the elements of the sequence differ from x star. So you can define the error at step n. So this is like how much like the nth term of the sequence differs from the limit. Okay. So this is, and you have to use absolute value because you don't know which one is smaller or greater than the other. So it's better to to compute that using absolute value. So this is measures how far the nth element of the sequence is that making sense? Like the definition. So like like a silly example of this. If like the sequence were something very simple, like 2 plus 3 over n, right? Like then we know that the limit, what is the limit in this case? The limit would be 2. So the error at step n would be xn minus x star, would be in this case 2 plus 3 over n minus 2. And this would be like 3 divided by n, which is just 3 over n, right? So that would measure how much like the nth term, you know, differs from the limit. And that is like a useful calculation to have because, again, like a sequence is like a process that like goes forever. So in practice, you can never terminate like a sequence. If you're using like like a computer program to compute the terms of the sequence, you know, you cannot compute the infinitely many terms of the sequence. So eventually, at some point, you will have to terminate. So you would like to terminate after you have like some amount, like some margin of error, which is like acceptable, right? So usually, you never get to the limit. You just say, okay, I'll compute the elements in the sequence up to an error, which is, I don't know, 10 to the negative 5 or whatever. Uh, it is. I mean, right. For that is true, right? Like for like a sequence that approximates, right? If the sequence converges, right? Since like you know the limit as x goes to infinity of the error term should be going to 0, right? Um, that's correct. Yes, because like you want the terms to approximate the sequence. So that is true. But the thing is, like, there are ways to there are ways of convergence that are faster than others. Because, for example, here's another sequence. Like, you could have another example. You could have like 2 plus 3 divided by n squared, right? Uh, the limit is still 2, clearly, but the error, right? Like the error in this case, what would be the error? Like that would, if you computed that would be 3 over n squared, right? And 3 over n squared, if you compare these two errors, 3 over n versus 3 over n squared, 3 over n squared converges faster, that shrinks faster. That's what I'm trying to say as n increases. So if you have two sequences, right, imagine that you have two sequences to approximate the number 2, which is kind of like a silly thing. But if you have two sequences that approximate the number 2, like this one or this one, this would be a better sequence to use because it would get closer to 2 faster, if that makes sense. Uh, So even it's true that in all these sequences, like the error goes to zero, but sometimes depending on the approximation scheme that you use, like the error could go to zero faster than other occasions. That's kind of like the idea. Is that making sense? So like the idea is that it can like the error. So depending on the approximation scheme, the error can can converge faster to zero than other methods, faster or slower to zero. So what I want to kind of like maybe do for maybe I'll finish it next time. But what I want to do for like a couple of minutes at least now is to talk about like convergent, like different convergence, like different rates of convergence for the error. So there's like a um, type of error which converges linearly. Um, And then there's another one that's called quadratic convergence. And so I'll kind of like explain about those two because those are the ones that appear um, in the methods that we have used. Um, okay, so here's like the first example. I mean, at least I will do at least just like the linear convergence today. Okay, so we say that converges linearly. So what does this mean? What this means here is that you compare like the errors, how the error of step n compares to the error at step n minus one. And if the ratio is like a constant, roughly, then you say that that converges linearly. Why is that? Because like it's better to kind of like write this down in terms of like the actual definition. Oh, actually, let me. So I mean, what this is saying is that roughly, it's like pretend that the limit is were not there, right? Like imagine that we had no limit here, in front of the errors. Roughly, what this is saying that En divided by En minus one is like a constant. It's like approximately a constant. Again, like I use this symbol whenever I mean kind of like that this is like approximately equals. So, in the limit it's a true equality, but before taking limits, that means that's roughly true. So in other words, what this is saying is that En is a constant times En minus one. That means that the error at step n is just like a constant rescaling of the error at step n minus one. So kind of like the errors rescale like linearly. Kind of like that's kind of like the idea because the ratio is just like a constant. Um, so in other words, like the way in which the next like the error at step n depends on the error at step n minus one. It's just like by a constant rescaling. That's kind of like roughly what's going on here. So that's kind of like like a very basic way of like converging to zero. In fact, that is for the first sequence that we were working with, that is like the linear convergence because let's do it for the sequence we were working with. So what is like the limit of the errors in this case? So that means that, if you compare the ratio for this sequence, if you compare the ratio of the errors, they kind of like scale linearly with one another, for example. So like that means like the error in the next step is not that like it just is a constant factor of like the error in the previous step. In this case, like the ratio happened to be one, but there could be other cases where like the ratio is not one. Um, Okay, so for example, in the fixed, like what I wanted to at least mention today is that in the fixed point theorem, the errors rescale linearly. So that's kind of what I wanted to discuss today. So let's consider the fixed point theorem. Let's consider the sequence for the fixed point theorem. And this was like the sequence we used for the fixed point theorem. So my claim for this sequence is that this sequence that we use for the fixed point theorem uh, like has like this linear convergence like of the errors or like or the terms. So what does that mean? It means that you have to compute the ratio of the error terms. Okay, so we have to estimate this limit. So what is xn? We have to use the fact that xn is f of xn minus 1. And this is also useful. What is x star? X star is f of x star because x star is a fixed point. Okay, so this gives you the limit as n goes to infinity of xn minus x star divided by. Is that making sense? Kind of like what I computed here. And then okay. What then hopefully like now the mean value theorem kicks in. I don't know if you remember the mean value theorem from Calc 1. Like it has been a while probably for most of you. But what did the mean value theorem say? Again, I don't know what the graph of the function is like. Okay, so this is a fixed point, right? This was a fixed point, so this is x star, although that I'm not going to use too much. I'm just trying to do it a little bit more accurate. So this is x star, that's a fixed point. Let me erase this to not make it too confusing. And then this is xn minus 1. Okay, so this is f of x star, and here is f of xn minus 1. Oh, actually, well, maybe it's right here. Okay, so if you remember what the mean value theorem says, is that the mean value theorem says is that there is a point, um, there is a point between these 2 points, like I mean, it doesn't matter which one is to the left of the other, where the the value of the derivative at that point is the same as a mean value of the function. So like this is like, how much the function, you know, this is like this is like the change of the function in f. This is the change of the function in x. So it's kind of like an average rate of change, right? Like this was like an average rate of change. And so what the mean value theorem says from Calc 1 is that this is the same as the f prime of a number Cn minus 1. Okay? Where Cn minus 1 has to be between xn minus 1 and x star. Where But you see, as n goes to infinity, the thing is that this sequence is converging to x star. So the Cns minus 1 are also converging to x star. So in the limit, this just gives you f prime of x star. So in other words, so the limit of the errors, and this is like the constant that you wanted. Okay, so that tells you that in the fixed points method, in the fixed point method, the the successive errors are basically if you take the ratio of two of the errors, that's roughly the value of the derivative at the fixed point. That's kind of what this is saying. So that gives you like an estimate on how much the errors like are approaching, you know, are like how much the errors are changing. Remember, like in fact, in the fixed point, the derivatives were less than 1 because it was a contraction. So like that tells you that the limit that's actually more interesting, right? This is saying that the ratio of the errors is less or equal to our constant of contraction. So if you had like a function that is a contraction, that tells you that the error, like the ratio of the errors cannot exceed that contraction factor, which is like a useful thing to know because it gives you a way to estimate, like how much after how many steps you will be within certain amount, of like the limit, which is like so it's like a more precise like estimate of the limit, basically. Okay, let's uh end here. I think it's like a good place to end. Like, I mean, I just wanted to illustrate this, like that, in practice, like when you create like all these sequences, it's useful not only to know that the sequence converges, but it's also useful to know that how fast it converges. So there are circumstances like in these methods where you can say by how much it converges, like how fast it converges. And but like this is kind of like an illustration that like it does require a bit more like analysis of how it converges. So it's kind of like just for you to have like an idea of like how these things are found. But I guess like these error estimates, like we won't really use them too much in practice. It's just like for us to kind of like know that if you wanted, you could find more information about how the sequence converges. So if someone is interested, if you look at the book, it also discusses the convergence rate Newton Raphson, which is quadratic. So the idea is that that one is a bit better. But I don't think it makes a lot of sense to do it in class because it's not much that we're going to use with it. But at least I wanted to have like an example so that you would see how these things are computed in practice. But it is, I think, a good place to stop for today. I'll stay around if someone has questions about anything as usual, but if not, I think we can end here. Um, oh, because remember in the fixed point theorem, you assume that the derivative was always less than k, where k was a contraction, right? Right, right. I should at least I should put it here for fixed point. We assume that the derivative was always less or equal to k, right? Yeah, I have been updating. I have been updating the practice problem sets every day, so they're more now on the PDF. I'll send an announcement later today about which problems you should look for, like the second quiz. But yeah, like if you have opened the PDF, like I posted some in the morning, some more in the morning. Um, I mean, yes, like you took you had taken like linear optimization with me, right, Ashley? I mean, it's kind of like the same. Like, it would be similar to like a similar setup, like, to like linear optimization. Like, so like from the problems on the quiz or like, I mean, we didn't have quiz in linear optimization, but it's kind of like the same idea, like the problems will be kind of like based on the problem on the practice problems. I mean, I will add some more here, but basically like what I'll do in practice is just change the numbers and that's it. Like, at least for the ones that are like computational, like because once you know how, like, that's the thing. Once you know like what the sequence is, you just apply it every single time. That's the beauty of a, like, algorithm, right? That every single time there's no creativity. Once you have the algorithm, you always do the same. That's kind of like the point of like an algorithm. So it's just like a bunch of like brute force computation. So I mean, if you kind of like, and I will probably I'll decide, but I'll probably give you some for you not to memorize. Like, I don't expect everyone to memorize all the sequences. There are too many that we'll cover. So some of them I'll kind of like just give on the quiz or the exam. Uh, Others, if they're too basic, then I may ask you to memorize them, but not all of them. Only like the ones that are really complicated. Like Newton Raphson. Like Newton Raphson is a bit more tricky, so I wouldn't expect people to memorize that one. I think the fixed point one is simple enough that everyone can memorize it. So like I'll kind of like do case by case. Um, Anyone? Oh, I think what I'll do is I'll finish doing some updates to the PDF between today and tomorrow I'll create like an assignment for you to kind of like upload some problems. Let me check problem 2.2. I actually don't know, but let me see. From pro. I think you're correct. So, yeah, like, yes, or it could be that, like, I think it refers to the third midpoint. I think that the only thing is like on the book, if you're reading the textbook, usually, the textbook starts at x0. Like the first element in the sequence, they call x0. I'm calling them x1, right? So by P3, like P3 probably refers to the, like, yeah, like it would be the third midterm. Um, like there might be like a plus one like shift in the sequence, but that's fine. Like like that's like So like if you didn't find that one, that means that you probably have to do one more step just because we may be like out of phase with the book by one step, because many times like the book starts at 0, which is convenient. I mean, where do you start the sequences at 0 or 1? There's not like, it kind of like depends on the preference. But yeah, like that could be like the only difference, like that you may need like another step. You know, if that's not the one that you found, like you probably need to do one more step, and that would be the one. Yeah. No, sorry about that. Yeah, I forgot to. I should mention that at some point, like during class. Although this is still being recorded, so if someone watches like the recording, they will see that. Anyone else? Any other questions?
I just have a quick question.
Mhm.
For like finding the constant, like the contraction constant, when you
Mhm.
say like when you say like you need to find if the derivative is less than one, like I'm a little confused because the derivative is a function. So like how do you
Oh well, I mean, like, you need to find an interval that guarantees that on that interval the function itself is less than one, right? So, let me see if I can still let me share can you see let me see if like the iPad. Okay, you can see the iPad, right? Um,
yeah.
okay, so for example, I think I had some like let me see one of the contraction problems that I have on the on the note. So like yeah, like okay, like let's do something simple, like x cubed plus x, right? So like I could ask you, where is that a contraction, right? Like when is this a contraction? One easy way is to make the derivative less than one, right? Now, if you find the derivative, that is 3x squared plus one, right? Okay, so this one is actually not going to be super nice because like this stupid one. So let's say just to make it like easier, um, okay, now this will be fine, right? Okay, so this gives you 3x squared plus one half, okay? And so that is a function, I agree with you, right? But depending on the values that you give x, that number that you see here, it could be less than one. Is that making sense? So, like, for example, like imagine that you wanted this to always be less than 9 over 10, right? Just for like, because 9 over 10 is less than 1, right? So I'm thinking of this as my k. Is that making sense?
Yeah.
Okay, so then that tells you in a way what values for x you should choose. Because if you want 3x squared plus one half to be less than 9 over 10, right? That gives you like an inequality to solve for x. Uh, so how much is this? Like 18 minus 10? Is that 8 over is that making sense? Like 18 minus 10, 8 over, right. So that tells you that x squared should be what? 8 over 16, right? Is that making sense?
Hmm.
So that means that if you happen to choose that interval, or like, I mean, if you take square roots, like you can kind of like, find that, like, that, I mean, well, I mean, I guess it should be what, between negative root of 8 over 60 and root of 8 over 60, that would work, right? So if you take x to be between those two values, right, that guarantees that the derivative would always be less than 9 over 10, right?
Okay. Okay, yeah. I understand now. Thank you.
But of course, like, well, you see, it's kind of like a bit of ambiguous because, like, then you do have to kind of play a little bit with the function to control the derivative. If you notice what happened, why did I put a one half here? Because if I had kept it without the one half and just with one, right, then like, I'm screwed because like that's 3x squared plus one. 3x squared plus one is never less than one, right?
Hmm.
So
Okay.
like
That makes sense.
that would never that is actually like an easy example. That function with the one like without the two, that would never be a contraction, right?
Hmm.
So
Okay.
and it's kind of like a game, like I will only give it for. I mean, I do like these problems because it's. I like when sometimes like the problems don't have like a unique answer. Just that people kind of like get used to that. So, but it wouldn't be anything for which you cannot kind of like play around with the inequalities a little bit to see what you should get. So, like usually it would have to be something like that ends up being quadratic, so that you can kind of like, or with logarithms or like exponentials, something where you can kind of like solve the inequality that you get. But that is like that is a way to kind of like make it a contraction in practice, if you see.
Hmm. Okay,
Yeah, yeah.
that makes
Yeah.
sense. Thank you.
Good, good. Anyone else? Okay, perfect. If not, I'll update some of the problems of the PDFs and all that stuff, but I'll send you some announcement after I have finished those updates, and I'll see you on Monday. That sounds good.